Hi friends, I am Snehal and today we are going to start with our next chapter of 11th standard physics, work, energy and power. And in this video we are going to see the concept of work, kinetic energy and work energy theorem for a constant force as well as for a variable force. But before starting, let me tell you that we are going to require the concept of dot product of two vectors in order to understand the upcoming topics. So if you haven't studied the dot product, please go back and study it. I have also made a video on dot product and cross product. So if you like, you can watch my video also, and I will also include it in the playlist of this chapter so that you can easily locate it. So now let's begin. So let us start with the definition of work, and let's see one-dimensional case first. So suppose that there is this cart resting on the floor and the cart is pulled with a string with force F. So initially the cart is at this point, let's call it A, and till the time this force F keeps on acting on the cart, suppose it reaches this point, let's call it B. So the displacement of the cart is from A to B, and let's call the displacement as S. So in one-dimensional case, the work done by this force F on the cart is simply defined as the product of force with the displacement. And now it's very easy to generalize it to three-dimensional case. So for three-dimensional case, let's suppose that there is some angle between the force and the displacement. And now, since we are considering a three-dimensional case, we need to represent the force and the displacement by vectors. So let's suppose force is in this direction, so it is F bar, and displacement is still along the floor, so let's call it S bar, and now there is some angle theta between the force and the displacement. So for this 3D case, what we do is we find the component of force in direction of the displacement. So let's resolve this force along two perpendicular directions. So component in this direction will be F cos theta. So F into cosine of theta is component in this direction, and component in perpendicular direction will be F into sine of theta. So now work is defined as the component of force in direction of displacement, which is F cosine theta, multiplied by magnitude of the displacement S, and by definition this is the dot product between these two vectors, force and the displacement. So this is equal to F bar dot S bar. Okay, so this is the definition of work for three-dimensional case, and if we just substitute theta equals to 0, what we get is the one-dimensional case. So we can say that there is no work if if F is equal to 0, so magnitude of force is 0, or S is equal to 0, or theta equals to 90 degrees. Okay, since cos of 90 is 0, and that means there is no work done if force and displacement are perpendicular to each other. Okay, So this is the concept of work. Then we'll see the work energy theorem for 1D case. So let's recall the third kinematic equation of motion. So we know that the third kinematic equation is v squared minus u squared equals to 2 times of a times s, where v is final speed, u is initial speed, a is acceleration, and s is the displacement. Now I can take this 2 on the other side and multiply each term of this equation with m, mass. So doing that, what I get is, so multiplying with m, I get mv squared minus mu squared equals to 2 times of m into a times s, and I will take 2 on the other side. So I get half of mv squared minus half of m times u squared is equal to m into a multiplied by s. Now what is m times a? So we know that m times a is the force F, and what is force times displacement? So we have just defined that the force times displacement is the work. So this is work. Okay. Now these terms on left hand side of the equation, half of m times v squared minus half of m times u squared, we call them as the kinetic energy of the object. Okay. So half of mv squared, since v is final velocity, we call this term as the final kinetic energy. Let's denote it by k suffix f. And half of mu squared, since u is the initial velocity or initial speed, it is called as the initial kinetic energy of the object. So let's denote it by k suffix I. And what we are looking at is the special case, the one-dimensional case of work energy theorem. And it says that the work done on an object is equal to the change in kinetic energy of an object. So let me note it down. The work done on an object is equal to change in kinetic energy of the object. Now this is 1D case, and we can easily generalize this to 3D case. So for 3D case, we know how do we find out work. It is just dot product of force and displacement. So for 3D case, work is dot product of F bar dot S bar. Kinetic energy is equal to half of m times v squared, and I can write this v squared as v bar dotted with v bar. Okay, the dot product of v bar with v bar. Okay, why? Because it is v, the magnitude of first vector, into magnitude of second vector multiplied by cosine of the angle between two. And what is angle between v bar and v bar? So it is 0, and we know that cos of 0 is equal to 1. So that's why this is equal to v squared, and therefore I can write it as v bar dot with v bar. But the form of work energy theorem remains the same. So work energy theorem for 3D case 2, it is work done is equal to final kinetic energy minus the initial kinetic energy. So now let's look at this term called kinetic energy, and we have defined kinetic energy of an object equals to half of its mass multiplied by speed squared. So question is, why it is called energy in the first place? So energy is defined as capacity of an object to perform work, and the kinetic energy we define it as the energy possessed by an object due to motion of an object and how it is responsible to perform any kind of work. So let's consider again the example of the cart. So this is a moving cart, and let's suppose it is moving with speed v in this direction. Now suppose this moving cart collides with this object. So when there is collision, this object will be displaced in the same direction as that of motion of the cart. So due to the velocity or due to the kinetic energy possessed by this cart, this object can be displaced. That means the cart will exert a force on the object and it will perform some work. Okay, and that's why we say that there is some energy possessed by this cart due to its motion, and we call that energy as kinetic energy of the cart. So that's the concept of the kinetic energy. So now we understand the concept of work, kinetic energy and work energy theorem for a constant force. So the next thing is the work energy theorem for a variable force. So let's see it. Now in order to understand the work energy theorem for a variable force, we need to know what is graphical representation of work. So let's try to represent the work done graphically. So let's see graphical representation of work, and let's see the case of constant force first. So what I will do is I will plot force versus position of an object. Let's call it x, and let's suppose we start from origin. So for a constant force, this graph will look like this. The force will remain constant against the position, and let's suppose the magnitude of force is F. So 0 is the initial position and x suffix F is the final position. So this length from 0 to x suffix F is the displacement S of the object. Okay, so this side of this rectangle is force and this side of this rectangle is the displacement, and therefore what is F multiplied by S? It is area under this force versus position curve. Okay, so this is the case of a constant force. So I can say work done on an object is area under F versus X curve. Now let's draw the graph for a variable force. So for a variable force, again force on y-axis, and position on x-axis, and for variable force, this graph between the force and position will look something like this. So let's suppose x suffix I is the initial position and x suffix f is the final position. So the length of this axis from xi to xf is the displacement. Okay. So what we do is we call this force F as some function of the position x. So f of x is the force at position x, and then to find out an area, what we do is we use integration. Okay, so we know that integration gives us area under a curve. So work is equal to area under f versus x curve, and it will be integration of f dot dx from this initial position x suffix I to the final position x suffix f. Okay. Then let's suppose that initial velocity or initial speed that is at position xi is equal to v suffix I, and final speed at x suffix f is equal to v suffix f. So the work done is integral of f dot dx from lower limit xi to upper limit xf, and we know what is force. So force is mass into acceleration, so we can substitute that into this integral to get integral of m into a dot dx from xi to xf, and then we know that acceleration is change in velocity with respect to time, that is derivative of velocity with respect to the time. Then let's substitute that too. So we get integral of m into dv by dt into dx from xi to x suffix f. Then what I am going to do next is called the change of variables. So we are going to change variable in this integral from x to v. So changing variable from x to v, and how are we going to achieve that? So for that I will take this dt in denominator of dx, and I will rewrite this as integral m into dv dx by dt. And what is dx by dt? It is change in position with respect to time. So dx by dt is the velocity, and we'll substitute that too to get m into dx by dt is v, mv dv. So we have changed the variable from x to v, that is from position to velocity. So the limits of integration will also change. So what was the velocity at xi? So at xi, the velocity or speed for 1D case is vi, and at xf the speed is v suffix f. So let's substitute that too. So I get integration, lower limit now will be v suffix I and the upper limit will be V suffix f. Now m is constant, so we can take it outside of the integration, and it is very simple integration to do. So integration from Vi to Vf of V dot dV. So integration of V dot dV is just V squared over 2. It is V squared over 2, and initial limit or the lower limit is Vi and the upper limit is V suffix f. Then let's substitute the upper limit and the lower limit. So substituting that, we get m times Vf squared divided by 2. So m times final speed squared divided by 2 minus m times initial speed squared divided by 2, substituting the lower limit. So now this is nothing but the final kinetic energy, and this term is nothing but the initial kinetic energy of the object. So we have work done for a variable force 2 as the difference between final and initial kinetic energy of the object. Okay. So work energy theorem for the constant force also holds true for the variable force.